Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing the theory of reliability, which is relevant or which is applicable to the reliability and the quality assurance of the spacecraft and its subsystems. So, just a quick recap. So, in the last session we derived this expression, that is the reliability function in terms of the failure rate or the hazard rate. And then we have seen whenever this H t is constant given by this, the failure rate is constant as seen here. So, you see this is your F t, it is not F t, this is actually H t, this is H t, this is H t. So, H t is constant. So, you can say this is your lambda. So, when it is constant, you can write the expression for the reliability function like this is as a exponential function, and this we say this is called the exponential probability function, and you can find the that is the probability density function F t, that is the probability density function for the failure by differentiating this. So, this will be minus of d r t by d t. So, you get lambda e to the minus lambda t. So, these are the things already we did in our last class. Yeah. So, this is the thing we did it. So, we will continue with this topic, that is the bathtub, which we discussed in the last session. So, and we will see the what is the failure rate and how to how to mathematically model those failure rate. There are 3 regions, and then we will define a very important term, that is called the mean time to failure, that we will write the expression for that, and then mean satellite lifetime. So, these are the topics I am going to tell you. So, you see here this I just mentioned about this, this is called the bathtub curve, and this represents the failure rate. Especially it is much relevant to the electronic system or the components, and this stage is also called the infant mortality. Infant mortality period. Okay. So, we will define this as T 1, then this is T 2 and this is 0. So, H t, this is H t, that is the hazard function or the failure rate, then I can write this H. So, H t is strictly decreasing. Strictly decreasing in the interval. So, 0 to t and t 1. Okay. Now, this is the region 1, and in the region 2 H t is constant. H is constant in the interval t 1 less than or equal to t less than or equal to t 2. And third, it is strictly increasing in the third region, strictly increasing when the time is greater than t 2, greater than or equal to t 2. So, now we will see that is if I because how to suppose if I want to write the reliability expression, or the mathematically I want to write the expression. So, then I need this failure rate or the hazard rate. So, what are those, what are the mathematical the model or mathematical function, distribution function you can use. So, maybe you have already come across the function, but I will mention it here. So, this is called the Weibull distribution function. Weibull distribution function, we will see it how it represents. So, Weibull distribution function which is a flexible function which can be used to model failure times and it can represent all the three regions of bathtub curve. So, it depends on the parameter, we will just see. So, you can have representation of all the three regions from this Weibull distribution depending on what are the the parameters you are using. So, it depends on the parameters of the Weibull function depending on the parameters of the Weibull function. So, we will just see it. We will explain this curve before I write down the probability density function. So, we can write the Weibull probability density function I will write it by f t. So, it is a failure, there is the probability density function of failure. So, I can write it beta by eta then t divided by eta to the power beta minus 1. So, we are using a 2 parameter Weibull function, there can be 3 parameter also. So, we are using only 2 parameter, then exponential minus t by eta to the power beta. Okay. So, where beta is the shape parameter and eta is called the scale parameter. And t is the time variable, random variable, t is time, a random variable. Okay. So, you can once this is given, so you can find the R t. So, R t will be equal to minus integration of f t dt, and using this thing you can find the that is the hazard rate, or so I will write it h t. So, I can write h t is equal to H 2 will be equal to f t by r t. So, once you put all this expression and take the integrations, then you can find this as this will be given by beta divided by eta, then t divided by eta to the power beta minus 1. Now, depending on the values of if you plot this h t as a function, so you will see that when the shape function, that is the beta, that is the beta is equal to 0.5, then beta is equal to 2, then beta is equal to 5, and here beta is equal to 1. So, depending on the the value of the beta, you can see that it will be when the beta is equal to 1, it is a straight line. Whenever beta is less than 1, so what is happening? It is decreasing, and the increasing case you will get when it is, when you get beta is more than 2. In this case, it is a linear, the distribution is linear. So, now you see how it is used. So, I will write it here, the value of beta, it determines value of beta determines failure rate behavior, determines failure rate behavior. So, when beta is, you have seen when beta is less than 1, so it is decreasing failure rate. So, what is this region? This is the infant mortality zone, mortality period. When beta is equal to 1, constant failure rate, and this is the useful life. So, failure can occur in this period only by accident or by coincidence, and when beta is greater than 1, so it is increasing failure rate, What does it mean? That it is a wear out. Okay. So, this is the Weibull distribution. So, there can be. So, as we have seen, that is that bathtub curve, that is the where the failure rate is not constant, we can represent it by Weibull function, and we said we can also express it by using normal distribution. So, let us write the normal distribution. So, normal distribution function or normal probability distribution function, which we will represent it for the end of life phase or zone in the bathtub curve, phase or zone of the bathtub curve. So, the components prone to wear out So, which are those components? So, components may be such as, that is the bearing used in rotating parts, then bearing, then the thrusters, the propellants in the thrusters, or the TWT tubes have failure rate at the end of life phase, at the end of life phase, at the end of life, which have failure rates that are no more constant. So, we can represent this probability of failure, probability of failure, or probability of failure, that is the distribution function. This is the distribution function can be represented by a normal distribution, can be represented by normal or Gaussian distribution. So, this I can write that the distribution function f t, that is the distribution function of the failure, by 1 by square root of twice by sigma square exponential where mu is the mean component lifetime. Component lifetime, and sigma is the standard deviation. So, I can write the reliability function R t is equal to 1 minus f t, where f t is the failure function or the unreliability function. So, this I can write 1 minus, so 1 minus t to infinity f t dt. So, this I can write as 1 minus 1 by sigma square root twice pi. So, already we have written this f t expression. So, just we are putting it in this expression. So, t to infinity, then exponential minus half t minus mu by sigma square dt. Okay. Now, H t is given by F t by R t So, we can substitute this R t here and we can find the H t. Now, one point here. So, we have already seen the bathtub curve like this. So, this is the useful period and or the zone, and this is the zone, it is called the infant mortality zone. This is the useful operating zone, useful life, and this is the end of life or the wear out, or the wear out period of the components or the subsystems. Now, this infant mortality, it can be overcome, overcome through proper qualification process on the ground, to proper or test and evaluation process on ground before it is launched. So, generally the electronic components are prone to this infant mortality, like the integrated circuits and a few of the electronic devices. So, what is done that a burn-in test, it is called the burn-in test. Burn-in tests are performed. So, what is a burn-in test? So, burn-in tests are performed in elevated conditions. So, this is performed in elevated operating conditions. It can be the higher temperature limit or extended temperature, higher temperature limit, it can be higher voltage, higher current, or the power, and these tests are done in the environmental condition, that is the in vacuum condition. So, this is called. So, if you do this properly, the burnout test, and those components which are successful, then this can be this infant mortality can be avoided, or it can be that can be overcome, that type of failure. Okay. Now, we will define a term, this is called the mean time to failure. Mean time to failure. An acronym is used, it is called MTTF. So, what is MTTF? So, or mean time to failure, this is the mean time t, we will take a variable t of the occurrence of the first failure, occurrence of the first failure after the operations started. So, we will define, so this is the mean time. So, mean time means it is something like the expectation. So, what is expectation? Here my variable is, that is the random variable is t, and if I know what is the distribution function f t, that is the failure that is the failure rate or the distribution sorry, the failure distribution function. If I know the failure distribution function, so I will be able to calculate the mean by calculating the expectation. So, what I mean to say that here the t is basically I am to calculate statistical mean. So, statistical means mean means I am to calculate the expectation. So, expectation, this is also called E t, this is the expectation, the mean value. So, I can calculate it by 0 to infinity t f t dt. Okay. So, now this I can write as 0 to infinity t. Now, what is f t? F t is actually minus r dash t. So, I can write it t, so minus sign I will take it out, then t r t dt, so r dash. So, now what we will do, we will use the integration by parts. So, if I use the integration by parts, then I have this t, this is the first function, then the integration of the second function. Now, integration of the second function, since it is the differentiation, so it will give me r t. So, if I integrate the differentiation, that is, then I get r t, and this I am to put the limit from 0 to infinity, then this minus and this integration by parts, that minus it will become plus. So, and then I get 0 to infinity, and then the derivation of the first function. So, if you the differentiate t, you will get 1, and this if you integrate, so you will get r t. Now, let us see about this term. So, what should be the value of this term? Now, we see at t is equal to 0. So, r t 0 is equal to 1. So, this value will be 0 at t is equal to 0, at t is equal to 0, this term is 0, t r t is 0. What about at infinity? At infinity you will have r t is 0, but here what happens, the way this reliability function it will decrease, you have seen the exponential function, and the time is increasing linearly. So, what will happen, this increase in the time, it is linearly increasing, whereas this is increasing linearly, and this is decreasing very fast. So, what will happen, before it reaches to very high value of t, the total, the product of this will come to 0. So, at t is equal to infinity, also I can write, that is t into r t is equal to 0. What does it mean? That is the MTTF is equal to MTTF is equal to 0 to infinity r t dt. Okay. So, now we will calculate it. This I will explain maybe in the next session. Today, now that just let us calculate. I have now my t, that is MTTF, mean time to failure, t is equal to integration. So, I have integration 0 to infinity r t dt. Now, let us assume that it is the failure rate is constant. For constant failure rate, as we have seen during the operational or useful period of the satellite. So, we can consider there the failure rate is constant, that is equal to lambda. So, then I can write r t is equal to e to the power minus lambda t. So, then MTTF will be So, if you integrate 0 to infinity e to the power minus lambda t dt, then you will have 1 by lambda. So, this is a very important relation we need to remember, that is for constant failure rate the mean time to failure is given by 1 by lambda. So, I will conclude here today, and in the next session we will start with this this figure. So, here you see that is the reliability has suddenly come to 0 at some. So, that is called the the maximum operating life of the spacecraft. We will discuss this and we will go further. Okay, thank you very much.